Okay. So now we're going to move on to the case with the non-nested structure. So previously we talked about nested, right? So monotone. But now more interesting, more general case would be a non-monotone. And so if it's a non-monotone, then for example, combining two surveys, right? If you have two independent surveys, independent, then X1 and X2. I mean, A1 and A2, right? So A1, you observe X. A2, you observe X and Y. Okay. That means we can, from each sample, we can compute the following Hurwitz Thompson estimator. So that means you can actually obtain three estimators for two parameters, right? So you have two parameters, but you have three estimators. So that means you can gain something. And so then that means you can actually construct a construct a linear model, general linear model. And notice that these two, this is independent, right? So this is independent. So that's why you can get 0. But Y1 and these two could be correlated, right? So this is a typical GLS linear model problem. So we covered that already before. The interesting part, okay, so that's no problem. So that means if you do that, then you actually obtain a GLS estimator. The GLS estimator of X, total of X is a convex combination of the two Hurwitz Thompson estimators, two independent Hurwitz Thompson estimator, and GLS estimator for Y is actually a regression estimator using the X GLS estimator of X as a population control. Okay. So that is actually about GLS, right? But we are not really focus. The focus is not about computing the GLS estimator per se. Rather, we want to construct the calibration rate. Okay. So how to do that? And then means we know the best estimator already, right? We know the best estimator already, which is on the right side. And what we want to do is to compute the weight that satisfies the equation. But if you use this constraint and put it in your calibration procedure, that means your weight depends on Y. That's not good. We don't want weight to be depends on Y. Okay. Because end of the day, we want to achieve some internal consistency. We want to achieve something like this, right? But if weight depends on Y, we don't have that. Okay. So that means we do not want weight depends on Y. So that means we need to. The problem is we want to use the first part of calibration and then make sure that the final estimator matches with the GLS estimator. Okay. So that, okay, then to achieve that, okay, for now, let's assume that we can construct, or we can express the beta. What is beta hat 2, by the way? Beta hat 2 is this guy. But this is essentially if you have a Poisson sampling, for example, then you can actually write it as something like this. psi I max one psi prime inverse. So if you have a Poisson sampling, you have a closed form. So that means you can actually call it QI. So so QI inverse. So you can basically write some sort of this. And then once you figure out what is small QI, then you put it in your calibration function here. And so construct the calibration problem. So construct the calibration problem, something like this. Okay. So you can see that this is what I want, right? We want. So, okay, what is A2, by the way? So let's go back. A2 is the data, part of the data that we observe yi. So it makes sense because we don't want to create a weight for A1, right? Because A1 is just outside. We don't have a measurement what we want. So if you are interested in estimating the mean of y, okay, then you want to construct the survey question for that, right? So that means A2 is our survey, okay? A1 is somebody else, I mean, some other agency, okay? So CSSM, for example, right, create what is interested in doing some kind of a survey. You have some particular, problem, research problem that so that we want to create, we have a survey questions already, but we realize that there's a other agency, right, from other agency has some information. A1 in A. So then what we really end of the day, what we really want is to construct a weight for us to use, right? So then we want to create the weight for A2. So that is the goal. That's why so this is in-house, right? In-house. A2 is our house. So we want to construct the weight. And the weight supposed to satisfy this constraint, right? We want the weight to satisfy the best estimator of total of x if applied to xi in my sample. That's natural thing to consider. And interesting part is that, okay, I know the design weight already, right? I have a design weight. So I know I should center it, right? So that omega I hat will converge to d to I if the sample size is large. But we want to use a particular QI on top of that so that the final solution can be something like this. And then good news is that if this particular weight actually is algebraically equal to our GLS estimate. So we want to show these two. One is this one, second one is this one. So this is the problem, right? The formulation. So this is the formulation of the problem. The claim is that the solution is this one. And another claim is that the solution satisfies this one. So then this one, once you show that, then you are happy because this is what you want, right? Because we know that best estimator of y, total y is the GLS estimator. Right? This is our goal. So our goal is achieved. Okay. right? So this is the problem, right? Problem or goal. The tool is that to figure out what is a QI first, and then put it to your calibration function, and then solve it. Okay, so the first the first component should be easy, right? Because we already did a lot of algebra of this kind of algebra, but let's do it one more time, right? Okay. Lagrange multiplier, right? So will be two. Okay, so that's first one. We want to solve it to zero. And actually you can make make life easy. You can actually so that means you can actually obtain something like di plus lambda. Oops, there's no I. This is your final form of the final weight. And then because of the calibration constraint, that means your weight should be, lambda hat should be something like GLS minus X hat whole bit times 2 because your summation is over A2. So inverse Xi QI. So that is the closed form solution. That is our, so the first part is proved. Second part, right, head yi is yi plus and then by construction this is p hat 2. So we are done because this is the GLS system. Okay. So that basically solves our one research problem, right? And now, okay. By the way, any questions? Okay. So this is one topic, right? I mean, we have a two, non-nested. So we have a two independent survey, and they have both. They have a common measurement, and then we want to combine information, and then come up with the calibration weight that utilize all available information. So that basically solve the problem. The only thing potential, past potential extension will be how we can avoid the negative weight, right? So that's a natural thing to consider, but I'm not going to cover it here. So now let's try to use this idea further and generalize it, right? Something like this. So, okay, then you may have a many different situations, but let's assume that okay, we have a three independent sample, and B and C has some extra information for part subset of X. Okay. So then you want to combine information still, right? You want to combine information and then construct the weight, right? So that is reasonable research problem. And then same thing. It's we can call it two-step calibration weighting. Where step one, you use GLS, right? You should use GLS and construct the best estimator, which we know how to do it already, right? So we know because the key idea is okay. Uh, using the data structure, missing data. So this is a kind of a missing data. I mean, planned missing data. And so given the data structure, like NRI, right? This is exactly NRI problem. So like NRI, you can essentially use the each subset to construct the best estimate, construct the design-based estimator and combine them. Okay, so you combine it, and then you can construct the best estimator of the X, and also you can construct the best estimator of Y. But the best estimator of Y should be the regression estimator with X hat GLS as a total, control total that you want to leverage. Then second step is what? Same thing, right? So I guess the second step is that, okay, now, since I know this guy, since I know this GLS estimator already, I want to construct a calibration weight that satisfies the calibration constraint to the GLS estimator. And then the only thing is that how to construct the objective function, but the objective function should be centered, right? Centered to the design weight. So this is this part, and this QI is the same thing, right? The same thing that we used to compute the compute this coefficient here. So idea is okay. Try to approximate this one as this one, something like this, and then use it to QI here, and then do solve calibration problem. Then this is should be the answer, right? It should be the answer. You have a design weight. This is lambda, right? This is lambda hat prime, and then xi qi inverse. So that basically solve the extension. So I didn't, so this basically this kind of problem we can use calibration, right? Now, this is a little bit more tricky. Now, what's the difference? So previously, this y is measured in here. In that case, calibration is a little bit easy because we observe all xi in sample A. Okay. So here, right, if I have this one, okay, in this case, I observe all x, so the calibration is easy to construct with the sample A. But now this example is a little bit more tricky because we have this one. Then we cannot really, even though I have information here, I cannot really use. Okay. So what should we do? That means I cannot really have the observation for sample B that I can leverage, right? So that means GLS steps should be the same. I mean, GLS steps should be the same. The calibration step, your x1. So you cannot really use x2 into calibration. This is, and I know that this is best estimator anyway. So that means so same thing, right? Same thing, but the only difference is that I use x1 only in the calibration construction. And that's best we can. Okay.
So basically, we calibrate the information which is like observed with y as well, right?
Sorry.
While my y is observed and the x which is observed with y, we will only calibrate x from other sources. Like here y and x1 is observed in sample B, right?
Okay.
We are only calibrating x1
Right.
from other sources.
Right.
But if other x is also observed in other samples, then we will not calibrate.
I don't care about other calibration, but even if I add the calibration, they still matches with the GLS estimator. So even if, okay, you cannot really gain anything better than this one. So there's no way you can actually come up with a better estimator than this GLS estimator. Right? So then my calibration basically matches with the best estimator. So even though you may wonder, okay, how about I calibrate on A1, and calibrate on C and whatever, and then try to utilize it sample B. You may think that, but that doesn't really help because this is the best no matter what. No matter what, you cannot do better than this one for X1 part, right? So that's a good question.
And also, I was wondering why it, I know because X2 is not observed with Y. So X2 will not help in predicting all, right? So that's why we are not calibrating X2 information. That is also observed in sample A and sample C. That is important.
This guy uses the information in A and C too. GLS estimator.
But not on X2. X2 is also observed in A and C.
But X2 information is actually combined here
Oh, it's not.
because of GLS. Okay, I see. So see. Yeah. So if you look at this, as long as X1 and X2 are correlated, we do it. So best estimator. So one GLS, and you may have a best estimator GL X2, right? They are correlated. So correlated means that it has information. So this guy actually, right? So I think Moshime's question is, even if you use this one, right? We actually utilize this information through GLS. Okay. So two-step method for combining information from several sources. It can be developed in a unified way. In step one, you compute the GLS for the common measurement. And step two, apply calibration weighting, incorporating the GLS estimator as a benchmarking constraint. And then that's nice. And then the one tricky part is this QI, determination of QI. So QI actually, so if you have a Poisson sampling, we know how to do QI. But for other designs, maybe you need some approximation. Because usually design optimal, right? Okay. Yeah, so this is the various covariance matrix of the of this guy. And this one usually involves a double summation. But you want to write it as a single summation. So that means that we need to do some approximation. Or you want to, you can change the definition of the variance covariance matrix as a model, including the model, then you may achieve some alternative solution. So that is QI is kind of mysterious. I mean, it's a kind of key to achieving optimality. And then, but even if you choose incorrect, somewhat inefficient QI, you still combine information. So that's not bad. So, and then to avoid the negative weight, we can also consider device. So that is the Caleb is working on this right now. Okay, so repeated survey. Motivation is to okay, this is a little bit different topic. So now we have NRI, like NRI, right? We have a time series. Year 1, year 2, year 3, something like that. In that case, so you have the same Y, but the Y changes over time, right? Because population changes. So then, in that case, could be several parameters behind this. So you could be interested in difference of the you could be really only interested in the difference, how the change, or you could be interested in overall mean, or you could be interested in the most recent mean. So they are different parameters. Okay. The optimality depends on the parameter. So that means there's no uniformly optimal design. Because see, so here's a point. Okay, let's consider estimation of this. Okay, so theta 1 is the difference. Theta 1 is this difference. Then what is the variance? Right? Because this is the mean. A difference, your variance of the head will be variance of this guy and variance of this guy and minus the covariance. And you want this variance to be low. Okay. So how can we make the variance low in sampling? Okay. Usually Y1 and Y2 is measurement in different time, right? Yeah, last year. So they could be correlated, right? You are right. You don't change dramatically, right? You change it little by little every year. So that means you have a positive correlation, right? But this is positive. Most of the cases. But if the sampling, okay, so then how we, so basically, but the covariance is actually achieved when you maximize the overlap, right? If you maximize the overlap, that means what? Okay, that means you actually use the same sample, right? You use the same sample and just change the measurement, right? Then the variance, okay, versus. So I guess that is the basically the idea. Or do you wanna? So it's more like this. So if you compare the two, which one will have a smaller variance? The left side is a smaller variance. Because if you, in the extreme case, if these two are independent, if two samples are independent, that means what? Your covariance is 0, right? If they are totally the same, then the covariance will be positive. So then you reduce it, right? So that means the best design. So the best design for estimating the theta one is the measuring the same people every year, right? Then you can see. So okay, if you measure the same people every year, like panels, that is actually called the panel survey. Some surveys, if you are selected as a sample, and if you happen to move outside other state, then the surveyor will follow up. Okay, so basically contact the same person. Then you basically the difference is only due to the change in their measurement, right? If you use a different sample, then you have actually confounding with the change in the structural change with the sampling error, right? Okay, so anyway, that is the point. And then another estimate is that if you are interested in, so this is plus and minus, now you have a plus. Okay, so that means what? If you want to minimize the variance, that means you want to this to be 0. So no overlap sampling will be the best sampling. So then this one is kind of a compromise, partial replacement sampling like NRI. So partial overlap sampling is the design where we so okay. So we t equal 1. So so if this is the same sample, then this is a panel, right? So I guess key idea is okay. Now we kind of a partition. And so we just have the same person here, but don't have this one. And then have some the other. So it's like so then this is new new sample. This is the same panel. So then this one is okay. So that basically some portion of the original sample we have a same overlap, but some others we have a new sample, and then idea is okay. Basically we are if you are, but now we are only interested in, so this is y. This is so y2 is our parameter. Y1 is not really interested, but they are strong predictor. So then basically idea is okay. Idea is we can basically use this one as x and do construct. So you use this one as a training sample and predict. So you kind of fill input. Okay. So then you have information. And then you have additional. Okay. So then that's the best way to improve the efficiency. But I will cover that next week. So that's all for today.